Lithuania from 2018. How it is administrated is administrated so-called book and claim principle. Then there is no need for physical delivery of green gases. Basically, a customer can buy from any country guarantee of origin and then claim that he uses renewable energy. So there's no need for physical energy flow. And it is the difference between this system and the system I will be talking. Guarantees of origin, they have standard. They have one guarantee of origin represent 1 megawatt hour. It's a standard. And guarantee of origin is valid for 12 months. And it has minimum requirements for attributes. So it should state energy source from which the energy was produced. It also should say who is energy carrier. It can be electricity, gas, hydrogen, heating, synthetic gases. And also guarantee of origin must show identity of installation equipment, location, type, capacity. Also, it should state whether a production device received investment support and what form, and also the date when the installation became operational and the date of issue of the unique identification number. So just to make clear that one guarantee of origin is 1 megawatt hour, and that megawatt hour has unique number. It cannot be duplicated. Now, certification is second form of certificates for guarantees of origin. And to talk about them, I need to show you bigger picture. So most of you know that in RED II, there's an obligation set for country members that in 2030, 32% of final energy consumption should be from renewable sources, and the same for transport of 14%. So how this could be achieved? So for transport sectors, for transport sector, it could be achieved using fuels produced from renewable energy sources, such as electricity, hydrogen, and biofuels, which cover biomethane, biodiesel, synthetic fuels. Now, how to make sure that this biomethane is sustainable? There's sustainability criteria set out in RED II. And in order to ensure that biofuels placed in European market are sustainable, member states are obliged to require economic operators in the biofuel supply chain to demonstrate sustainability criteria have been met. Meaning that economic operators must participate in voluntary schemes, receive certificates, and in this way make sure that they produced biomethane is sustainable. For voluntary schemes are approved by European Commission, and for biomethane, it's two major certification schemes. It's ISCC EU and REDCERT that issues most of the certificates. How the system works. So on the right, you see that it's an example of REDCERT. REDCERT is in the middle. It basically receives recognition from European Commission. It contracts certification bodies. These certification bodies must be accredited by national authorities. And in the bottom blue box, you can see that the certification schemes covers all value chain. It covers value chain from raw materials up to the end user. And in every step, the suppliers or biomethane producers, they must be registered with REDCERT, making sure that they follow their requirements. Certificates are issued for biomethane plants once a year. Every year it is recertificated. Producers, when they receive certificates, when they produce biomethane, they produce biomethane in consignments. So every consignment, meaning that consignment has characteristics. For that characteristics, such as CO2 emissions, they issue proof of sustainability document. This proof of sustainability document, it travels from biomethane producer up to all that value chain in the blue box while it receives a final customer, meaning that every step is documented and all the CO2 emissions are accounted. Also, this proof of sustainability requires mass balance principle. As I spoke before, for guarantees of origin is book and claim, meaning that you can buy guarantee of origin in one country, cancel in another. In this case, you need to follow mass balance. Means that when the biomethane is injected into the gas grid, it has to be recorded. Also, when it's withdrawn, it has to be recorded. And when it travels from one country to another, the capacity bookings on interconnection points must be booked. Now we have two certification schemes, guarantee of origin and these certifications. And there is a problem because in some countries, because we have two separate independent existing systems, and in some countries there is even more these systems because we have their own national systems. These systems has different purposes. Guarantees of origin is purpose for disclaiming. Certification scheme purpose is to achieve national renewable energy targets. And it could be so that same biomethane producer, it can register in national guarantees of origin register, and it also can register in the voluntary scheme. And guarantees of origin system administrator might not even have a clue that the same participant is participating in different scheme, meaning that the same amount of energy can receive two certificates and be traded separately. That means double counting, which is major error. What is the solution? So solution is to link these two systems on national legislation and introduce additional attributes on guarantees of origin, such as CO2 emissions. There is also initiative in Europe, it's regulated in the RED2 that union database must be established on European level, meaning that all the proof of sustainability, not biomethane, also for liquid and gaseous fuels, must be registered in one European database. The project is ongoing. It should start this year, but the role of guarantees of origin is unclear. So we had done this linking of guarantees of origin and proof of sustainability in Lithuania. How it was done, alternative fuel law was established last year. It set obligations for fuel suppliers to reach certain targets by certain years. And to reach this target, renewable fuel statistic unit system for liquid and gas fuels were established, meaning that every gas supplier, every fuel supplier must register in the system, and he covers these obligations using statistic unit system. So all the renewable fuel that was supplied, they receive certificates, and they register the certificates in this fuel statistic system unit. Then these certificates are converted from megawatt hours to megajoules, and 1 megajoule is one fuel statistic unit. Also, natural gas suppliers, they, according to this law, they can cover the obligation using guarantees of origin and proof of sustainability, meaning that we are tracking by guarantees of origin the movement of the green gases in the transmission and distribution system, and the proof of sustainability is covered by voluntary scheme. So we merge these two systems into one for transport sector purposes. And once these obligations were introduced, it boosted biomethane demand in Lithuania significantly. So as mentioned before, on the left is mandatory attributes for guarantees of origin, and on the right, it's additional attributes for proof of sustainability documentation. So it's calorific value, materials, also voluntary scheme name and unique number for production plant, and proof of sustainability document number and CO2 emissions. What is biomethane demand potential and general development in Lithuania? So according to National Climate Change Plan, the demand for biomethane should reach 1 terawatt-hour in 2030. It mainly for the transport purposes, but now it's seen that biomethane could be used in other sectors to cover CO2 obligations as well. Potential, it's accounted that potential to produce biomethane from manure varies from 0.4 to 1 terawatt-hour per year, and all potential for biomethane is about 2.2, 2.6 terawatt-hours per year. There is also investment support for biomethane in Lithuania. There is a program from National Climate Change. It was 15 million euros for 8 biomethane production plants, and there is second initiative from Recovery and Resilience Facility for period of 2022-2026, 22 million euros. As there is no biomethane production in Lithuania yet, but the demand in the transport sector is already rising, so biomethane together with guarantees of origin and proof of sustainability are physically imported from Netherlands. It is expected that this year we will import around 60 gigawatt-hours of biomethane, and also it's rising interest for guarantees of origin without proof of sustainability for other sectors. Regarding production, so first biomethane plant is already connected to transmission system. It should start operating already this month, and it's expected that this year it will produce 80 gigawatt-hours, next year 122 gigawatt-hours, and it will be one of the biggest producers in the region. We also have several more biomethane producers. We already have contracts with them, just we're waiting for them to finish construction working, and we expect that in 2030 we should reach about 2 terawatt-hours of biomethane produced annually. The problem for demand is that there is not enough biomethane filling stations, because these filling stations, they have to be connected to the grid. So most of the biomethane that will not be used in Lithuania will be exported to the other countries, and we already see that today. What are the challenges? So one of the challenges that there is a problem with biomethane producers who are far away from transmission system. They would want to receive guarantees of origin and proof of sustainability and to participate in the transport fuel system, but as they are not connected, we cannot issue guarantee of origin, and we are looking for the opportunities how to integrate them into guarantees of origin system. Another problem is that in all Europe there is no single guarantees of origin or proof of sustainability documents exchange system. So we have two competing bodies with different countries, meaning that if you want to exchange with all Europe, you have to join both organizations. And yeah, it's problematic. Second problem is that union database is coming into the game, and the guarantees of origin, the future of guarantees of origin is unclear because it's not clear how it will interact with union database, because it will collect all proof of sustainability documents, leaving guarantees of origin somewhere away. There's also interest from market participants to integrate bio-LNG into the guarantees of origin system, or at least into renewable fuel statistics system. And we also have several pilot projects for hydrogen. Hydrogen will be blended into the national gas grid, and for this hydrogen, we will issue guarantees of origin. So, yeah, so we will integrate hydrogen into guarantees of origin system. Thank you. Do you have any questions?
Thank you very much for that. There definitely were no questions, were there? Yeah, okay. And we come to our next speaker this morning from Emerson Automation Solutions, also in Lithuania. Algirdas, please. Thank you. Yes, coming down.
Good morning, everyone. My name is Algirdas Čebatorius. Thanks, Simon. You did very well with my name. I know it's a complicated one. I'm representing company Emerson, and we are, I would say, a global automation leader. My job is I'm a sales director for Poland, Baltics, and Ukraine, working on emerging industries and sustainability programs. Basically, this is why we are here. And we did a small change for our plant presentation. It will not be me alone. I know I can look boring. I got my colleague Darius Janas, who will help me out on the later stage. So we already figured out that there are quite good, let's say, he's already experienced with biomethane, biogas, or renewable natural gas, whatever name we will put on that, throughout Europe, and as well some nice installations in Poland. So we know that there is waste which can convert it to the energy, which is great. Also, Mindaugas did a great job with all these certificates of origins, and one of the crucial and key points in all of those installations, of course, is to have waste, then to have technology, then to have certificates. But if you want to convert it to the money, you will need automation for that. You will need accounting, quality, and other systems, which are crucial, and you need really reliable and accurate. So that's where we are. So I will start briefly. Who is Emerson? And Emerson, on these days, we are facing, I would say, a major change throughout the history of the company. And the history of the company is very long. And you will see that later on. So we are seeing that automation technologies are becoming more and more crucial, and even going into the higher level of the operations, into the information technologies. So we are under the conversion of the company to be not only automation but also software company, and that's basically the change which we are seeing, and the message from our CEO, Lal Karsanbhai. So a little bit briefly around Emerson, more than 130 years history. Of course, there was more changes within the company. We are a global company, founded in the US. We are smaller now, only like 70,000 employees, around 14 billion in terms of sales, and we are just everywhere. We are proud being also automation and software company. As you see, there are business segments over there, which is the newest acquisition of us is AspenTech, I would say a leader in terms of industrial software, digital twins, and manufacturing execution systems. And we are just everywhere with rich experience all over the place. If we look on our business, so as I told before, there are basically two pieces of the business: automations with intelligent devices, and software and control. And it's really crucial to get them connected. If we look into our sales by geography, as American company, not a big surprise, majority of the business is still in the United States, but this share is continuously shrinking, because other world areas are catching up very significantly, and we are getting better and better all over the world. Around 13% of our business comes from software on these days, because to measure and to have measurement or to have control, it's not anymore. You need to employ artificial intelligence or digital tools which can help you to work with that data which you get from your process. And we are presenting all of the markets, I would say, if we talk about general industries, discrete, power, and renewable. Especially renewable sector on these days is growing really, really significantly. We are in Europe, we are around 20,000 of employees, almost all over the Europe, just almost every country, I would say. Here in Poland, we are close to 1,000 employees. Here we have manufacturing location and several sales and service offices around the country. I will not dive deeply into that one. And as you see, 13% of the business is software, and majority of the business is intelligent device. And if we look throughout our portfolio, we have tools for safety and productivity. We have solutions for discrete automation. Measurement analytical devices, which are crucial for renewable industry. Then, of course, control valves and final control devices, and of course, control systems, and going up to the corporate level of the software throughout DCS systems. And the software part is growing significantly because of digitalization, basically. I talked on the beginning about the change, so basically this is all about the change of the company. So we have the divestitures of the company lately, and the newest one was divestiture of climate technologies. That's one of the, I think, biggest divestiture in the Emerson history. And of course, we got money out of that, and we invested. And mainly investments are going into the emerging industries, where we have companies, software companies like Fluxa and Micromine, who are active in metals and mining industry and pharmaceutical. And AspenTech together with Mita. Mita is a Danish company who is working mainly with wind energy and making solutions to make those wind farms, especially old wind farms, more efficient and optimizing all the wind park, not looking to the turbine as a one generating point, but looking to the whole wind park as a one homogeneous system, which should not disturb each other. And AspenTech, as I told already, a software company. And we will keep growing into various technologies, because Emerson is investing into the technology to make broader portfolio. Our references, they speak about themselves. Around the world, we have around 60,000 wind turbines. 19% of nuclear reactors are controlled by our technology. And we are #1 in terms of renewable diesel refinery, the biggest in the world. If we look in other market presence, so COVID was a really crucial point. So I would say 3 COVID vaccines produced using Emerson technology, and there are not more of them. And 24 out of 25 companies, they are using Emerson technology. I'm talking about big pharma companies. Huge install base and big. And that's because of our mainly really technological innovation. And we started many years ago from analog going to digital, and there where you see the devices like pressure transmitters and valve controllers and our control systems with millions of devices sold. Then from centralized control in the plants, we go to control in the field. And this is very crucial technology in terms of renewable energies, because you have many small sites all around the country or even continent. And in most of the cases, they are manless because they need to operate by themselves. And that's where, and you need to still keep the safety and efficiency and operate it safely. So then also, as projects are changing, you can't reinvent the wheel every time you do the projects or every time you do. So that's where we have really invested from off-the-shelf technology that you can buy some piece as a simple product, which has life cycle services, maintaining and everything. And this is, I think, crucial for every industry. And recent changes is related with operational and maintenance, and because I think most of the people who are from industry really remember the time when we've been running till failure and then fixing. It's too expensive, in my opinion, and everyone is seeing that. So now we need to talk about predictive maintenance and predictive diagnostics. So basically fix the problem before it occurred and plan as much as advance. So that's where we are as a company. And of course, of all these climate changes, we launched several years ago the environmental sustainability framework, which consists basically of 3 factors. As a global company, we do have manufacturing locations, factories, offices, service operations, so we are not saints, we are also polluting. So that's why we focused on ourselves as well, because if we talk about sustainable technologies with our customers, the best example you show is yourself. So greening off is basically we are looking to all our supply chain and all our manufacturing locations and all our operations and trying to and making them year by year more and more sustainable. Then if we took the next pillar, it's greening by. So that's where we work with our customers and trying to increase their energy efficiency, help them to change the feedstocks, help to change energy resources, and optimize current energy consumption with our technologies. And greening with is events like that and collaborations with various science institutions in investing into new R&D solutions and trying to make it. So this is basically our full strategy, which I would say represents really big portion, huge portion of our activities in terms of business and in terms of our activities. And some numbers. So we as every responsible company, we have our targets for ourselves, and these actually match global targets. I think the 2030 is our aim to get our own to net zero. I mean, our own operations, and 2045, we want to make zero throughout all supply chain, which means also our suppliers and all the chain of the supply needs to be totally net zero. And that's where we are aiming as every company, because you can't start the change without changing yourself. So by that, let's switch to the major topic, and let's talk about some calls renewable natural gas, and really, if I would look to the whole supply chain, and we look even quite short term, 10 plus or something that year, I think these biogas or biomethane or renewable natural gas, it is the easiest switch for any industry. Really the easiest switch, because you don't need to change your site too much. You don't need to change, you reinvest, because if power plant is fired by natural gas, it can be fired by biomethane without any investment, just changing the feedstock. So that's why I see really future, and it's going. So if we look to the all the supply chain, of course you have all this, you know, agricultural waste, then biogas plants, which we've seen already this morning, and then from biogas you can, as I told, use this gas for heating quite easily for electricity, or we are talking about upgrading that. And upgrading that means either you inject into the transmission system, into the gas network, or you liquefy it, or you compress it and use as a fuel. It's only the matter of where you need them and how you need them. And having those green certificates, you can really reduce your emission footprint very much. And we will focus, as we heard this morning, you need to have certificates, you need to have feedstock, but at the end, what I was listening, we talked about megawatt hours, megajoules, and quality. And that's why we focused mainly here on the injection station, and injection means also custody transfer station and custody transfer solutions, where you need to ensure your final product, which is biomethane quality, because you can't have low calorific value. You can't feed into the grid something what is not regulated, because there is around many European regulations as well as local regulations. Even you can't liquefy and can't put in your ships or transportation system anything. So here we talk about usage. So basically, if I would look throughout the region on the projects, the major challenges of those are gas quality, and you need to find out about your biomethane quality as early as possible, prior compression, prior liquefying, to send it back and maybe make additional cleaning and things like that. So this is one of the quality of one of the crucial points in the whole supply chain. Safety and efficiency. For me and for us as working on heavy industry for decades, this was something natural and normal. But if you take our classical power plants, refineries, there are working professionals. And if we come to the biogas market, you come to agricultural plant where actually you meet people who never before had any touch with natural gas, with explosive areas, and with things could explode, basically. So safety and making safety for them, it's really a challenge, and there you need also reliable partners to consult you. Also, I know that even just lately, a couple of months ago in Poland, there was some ease of legislation about biogas plants built or the ones which we will be built in the agricultural areas. So there is some kind of ease of legislation. But this is crucial. And another point which I could share from Baltic countries mainly, if you are building biogas plant and you are thinking where you are going to put your biogas or biomethane, still too much customizable project gives you quite high costs. And if you come to transportation system, you have all these quality system requirements and everything. We see different requirements varies by country, and usually this customization really increase the cost. And if we talk about liquefied biogas, that's even worse, because if you build a really micro plant, liquefying as a technology, it's quite costly. So you need to make sure that you are big enough to have a good return of investment. And one of the cases to simplify the systems as much as possible. So that's how we address when we go into that. So first of all, you need to comply with European standards, local regulations, safety regulations, and if you build custom, it's always a challenge. So standardize as much as possible, and standardization also gives you much lower complexity of your project. And I'm talking in terms of not only during the investment and building phase, but also later on throughout the operationals where you need to maintain and run. So simplifying the systems helps a lot. Safe production, this is another challenge which needs to be addressed, and because if we talk about biomethane, immediately the areas where you produce that becomes potential explosive areas. So you need to establish into your plants additional safety regulations, which were not so used before if you've been just a farmer before. You don't do that. You had different safety regulations for sure. And life cycle cost increase. So if we look into this value chain, we already see the biogas plant, then storage, then we talk about either compressor, liquefaction, or injection. And the major point is injection skid, which we will focus there, because there we will talk about custody transfer, about your quality, about system which can make you money. And with this point, I invite my colleague, which will take over from me, Darek Janos, and he will dive into a little bit deeper details.
Good morning, everyone. So we're trying to build something which will be modular and flexible, because these plants are smaller or bigger. That's the differences are quite high between them. So that's why we are trying to fit to or build something which will be modular and flexible to fit in the local requirements, which, as Algis said before, different in the different countries. So that's you can see on this picture total system which is required to measure what you sell. Yeah, it doesn't matter which type of the product you will choose. Yeah, that will be liquefying, or that will be CNG, or you inject the biogas to local grid, or you inject the biogas to network. Doesn't matter. On the end, you will need this part which is on the top, and the rest is depends from the local requirements. Yeah? So normally that looks like that. So we build few such a installation, and you can see that is the few parts, and the main parts is the control of the flow and pressure. Of course, that is a safety part, the shut valves, and that's everything is built on the skid. And eventually, we've got in this building where all these things are installed, we've got another part which is safe zone. This is also depends from the local regulation, yeah, because when we've got this biogas, we've got explosive zone, which creates some special requirements, yeah. And if we would like to avoid this zone, time to time we build a special wall, which is protect another part of the building between this zone, and in this part we can install the normal devices. When we regulate this flow, keep the pressure on the end, we must sell product. Yeah, we are not selling the cubic meters, we are not selling the kilograms, we are selling the energy. Yeah? So why do we have so many instrumentation for that? So as you see, we've got the flow meters, different type, because that depends from the local requirements. After that, we've got the quality control and calculation for the energy. Yeah? That is GC and flow meters together made this product, let's say. Because on the end, you've got this kilowatts or megawatts, doesn't matter what you want, but the calculation is made from these two instrumentation. And time to time, so we've got additional requirements like quality of the gas, how many sulfur components are in the gas. That is should be controlled. That is also made by this instrument, which is GC on this on the down. So finally, if you inject the biogas to local grid, that is required some authorization. And that's you can see that this compact authorization station, which can be installed also in the same area. And in this moment, you've got complete system to inject the gas to local network and calculate how many energy you supply to this network. What is the requirement for all this instrumentation? So the main, that is again flexibility, because the best is to sell this product when it's needed. So it means in the peaks. So morning, evening, and time to time, some time which is needed. And normally you supply so very low volume. And normally in the peaks you've got 100 times more than non-normal operation. That's why do we need so flexible instrumentation. And everything what I showed before, and this instrument, that is flexible from very low level of flow up to 1,000 cubic meters. So that's our idea to build such a system. On the end, because today everything is digitalized, we've got some software which can apply you to use the system from the desk and the home. Yeah. Normally, these plants staying in the fields in the middle of nowhere, and that is one or two operators which are feeding the system, and that is his job, yeah. And they don't know what is going on there. Usually, that is my experience from these plants which are existing in Poland now, and that some operator is sitting somewhere and he controlled from the home what is going on. So for all these things, you need reliable partner which will take your hand and move you through this process. And we can show you additionally what we did in different parts in Europe. So that is some example from the south part of Europe. You can see the real installation in the field, that we've got the few things there. So as you see, that everything is in the one container, and that is on the picture is shown the GC part. And here is the France, where we signed a nice contract for supplying these metering stations. As you can see, that is a lot of them implemented in these grids. Yeah. And of course, if you liquefying this, we've got also that's the solution. And so I can say we've got the nice contribution for the liquefying LNG, not liquefying, for LNG market in Poland. So we made a lot of installation. We've got a very good experience, and we've got in our company meat officer on our board. Then you can. He can do all needed documentation for all settlements. Yeah. So thank you. Do you have any questions?
Thank you very much. Great. Thank you. Thank you, gentlemen. So I think, I'm just looking at the time. Again, thanks very much, gentlemen. We come to the next part, which is the signing ceremony, the Memorandum of Understanding for Cooperation, which I'm handing over to Pavel, He will come down and no doubt he will explain how this will go ahead. Thanks.
So, ladies and gentlemen, I hope you had this one. Okay. Hello? Yeah, okay. Ladies and gentlemen, dear guests, thank you very much for being here, first of all. I hope you enjoyed last day. One of our main elements within the project of liquid energy is not only doing good things, not only showing technology, but also creating platform for cooperation for the future. I suppose it's quite obvious that the topic that we focus on is one of the main elements for the future energy market, or could be one of the very important elements of the future energy market. And during the whole 3 years we were working together, we started our cooperation. We have recognized how important it is to go on with this subject. And just after our internal discussion and discussion with our external cooperation partners, we came to the conclusion that it is important to go on, to move on with our cooperation. And because of this, we have decided to sign Memorandum of Understanding for Cooperation after projects and for the future. And we should, or we will focus on creating a bio-LNG, LNG market on micro nano scale. We would like to promote business. We would like to promote regional socio-economic development, and somehow I suppose we found a joint common interest. We have recognized that there is still something to do in the coming years. I suppose it's not a top secret that the situation nowadays with the energy crisis, with war in Ukraine, with change of paradigm, with all elements that are crucial for ensuring energy supply to the end users. So this is some kind of introduction, and I'd like to ask our first signatories of the memorandum. We belong to this this group as well. We already know that there will be next parties, next organizations that are willing to sign this memorandum. However, this will still take a few weeks because of the formal procedure. And now I would like to ask you to say a few words about your intention, about how important it is for you to go on with the cooperation. And Last but not least, from my side, I'd like to thank you, Grażyna Pasikowska-Sapota, our leader of the project. So a big applause to her, please. Thank you, thank you. Because it wouldn't be possible to implement liquid energy project without her. I do really appreciate your effort, your support, your work, your time spent on coordinating our activities within the project. I also would like to thank Mate Salok, is somewhere here. Mate, thank you. Applause, please. Thank you, because of course, this is the second part of let's say, conditions that are necessary to be fulfilled to make such projects happen. So thank you very much to Interreg South Baltic program for financing or co-financing our project. And I do really appreciate your effort, Mate, your work, your support, your readiness to solve all problems we had. It was really a pleasure to work with you. So now I'd like to ask you, Grażyna, just say a few words.
Thank you very much. On behalf of myself and Maritime Institute, Gdynia Maritime University, which is a lead partner of this project, I also would like to thank all my partners for support for the work in this project. I hope that we will finish at the end of this month our project with success. Thank you.
Yes, thank you. This project gives us a possibility to... This project gives us as engineering partners the possibility to bring out our knowledge for cryogenic fluids, for renewable energy into practical solutions. And I hope that we worked in the next time together to bring these solutions not only for the scientific mind, also we bring these solutions in the market for using for all peoples for renewable energies.
Thank you very much. Good morning. I think for us at the Rural Electrification Agency, we definitely look forward to an exciting opportunity to be able to demonstrate a market that can utilize biofuels technology, both from the production as well as a distribution perspective, and ultimately to power generation, and to be able to use that as an effective demonstration of a nano or mini scalable market opportunity, especially in the global south. Thank you very much.
The last 3 years have shown that we have built a reliable cooperation. We are a good team working together, and that shall be taken into the future. And I love to be a partner of that.
Thank you very much. Thank you very much. And now, paparazzi, please. So, yes, please, because sorry, I couldn't find you. Our official representative of lead partner Maritime Institute, University of Gdynia. So, please join us. Do you want to say a few words?
Yes. Good morning, everyone. Good morning. I'm the representative of management of Maritime Institute, responsible for finance. So I'm glad to be here, and I'm glad to collect some money, to prepare some money to financing this crucial and important activity. Thank you very much.
Okay, thank you very much. So paparazzi, please now, because we would like to have a few nice pictures. So first of all, Governor, you are the first. Okay. Let's do it like this. Okay. Thank you very much, and may I ask you to sign the memorandum of official. It's going about official signature, official formal signing of this document that is an agreement on cooperation in the future, in the next few years.
So just so you're aware, of course, it's an MOU. They're not signing their lives away for any reason. And I think that a copy of this MOU, I think, will be available for you to see later, to see exactly what is the content and what they have signed up to. Hopefully each individual has also read it themselves. And it's a very symbolic thing, I think, which doesn't yet close the conference, but very symbolic as we come to the end of the liquid energy project as well. So well done for organising that, Pavel. So big deal.
Thank you very much. We are looking forward for next steps. Even yesterday night and today morning, I spoke to Michael, and I know he spoke with the CEO of the Nigerian Rural Electrification Agency, and there are already next steps to be planned, to be implemented. That's why I do really appreciate that you would like to join us in this journey for next years. So thank you very much.
So I think we've finished slightly ahead of a schedule, which is fine. So we will now have a break for lunch, and we will gather again at about 1:15 for this afternoon's session. There's a training session, of course. We also have a coffee break, which is a luxury, and then we'll end with a plenary session. So thank you very much, and we'll see you later, 1:15 back here. Thank you. So, welcome back. Hope lunch was okay for you. We're going to continue in a moment with the next part, which is training with Marcin and Stefan. Just what I want to mention is there's a QR code here. If you follow that QR code, you can go over to YouTube and you'll see a number of videos from the conference. So it's broken down into talks, the different sessions. They were being uploaded last night because I saw them on my feed. And also this morning's are there also too. If you don't use the QR code, you can go on Liquid Energy on YouTube and you might see yourself there if you're a speaker, or you might see yourself in the crowd. Maybe you don't want to see yourself. But it's worth looking at. Really good quality, I have to say to Artur. Well done, Artur, for uploading them so late last night. I think I even saw one at 11 o'clock or 11:30, and also early this morning. So if you're interested, use the QR code. Or, as I said, head over to YouTube, search for Liquid Energy, and then you'll find the videos there. Okay. So I'm going to hand over now to this training part with Marcin and Stefan, please. If you could come up. Thank you.
Okay, good afternoon, ladies and gentlemen. My name is Stefan Jankowski, so I start as a first. And I'm representing Maritime University of Szczecin, Faculty of Navigation. My main field is maritime traffic engineering, but we were asked to prepare training because we take a part with two projects, Martech LNG and Go-LNG. And I'm sorry for all, because the training was prepared for wide spectrum of audience, so from students to the professionals. So I'm sorry for the points which are obvious for you. Okay, so for the last few days, 2 days, we heard about the market, about the business, about the opportunity, model business, and so on. And today, with this training, we want to approach you a little bit more the fuel itself, this LBG, liquefied biogas. So we talk about the properties, we talk about the hazards. So that part is mine. Okay, so the biogas is environmentally friendly, renewable source of energy. And it's come because all organic matter decay anyway. So producing methane, producing CO2. And by gathering these gases, we can, first of all, produce a fuel, renewable fuel, and also save our planet because of reduction greenhouse emission. And for example, in the United States, every year, 31 million of tons food waste are discarded in the landfills. So this amount of biomass producing also CH4, so methane, and CO2. Okay, so we can reduce this emission. Okay. The biogas can be used also in the circular economy, and so, for example, in the landfills, in the agriculture, all organic matter when it's producing on the farm can be used as a biomass. The biomass decay, we can produce methane, which can be used to power the machinery or to heat the building. But yesterday we also heard that this is not the most efficient way for using it. So the best is to make a pure, because as we see on the next slides, the compositions of the biogas, the raw gas, is quite low with methane. So we can remove all impurities, and then make almost pure methane. So, simply says, we have to produce biogas, we have to have the source of this organic matter. We have delivered it to compartment, the closed compartment, where without oxygen and with some kind of microorganisms to speed up the process, we can decompose this biomass. And the all gases which is gathered above surface are then go to the tank, and we can use it as a fuel. The rest of the biomass can be used in other way, like for example fertilizer, and we heard about this also yesterday. Biogas and biomass are both biofuels and are both renewable source of energy, but for biogas, the biomass is the raw material, and in this case, biogas is the end product. And there are few directives, European Union, which describe this biogas as a renewable source of energy. So both here, biomass and biogas are this environmentally friendly source of energy. Okay, we heard also that there are different kind of waste which can be used for producing biogas, but we can see that about 60% of this production, the gases, when we decompose this biomass, is methane. Then about 30% is CO2, then nitrogen, some amount of oxygen, and also quite a lot of HO2, so water. And some other residuals, which is very small amounts. So that's why using locally as a biogas to power the machinery and heat the houses is not so economic, because the heat power is quite lean, yes, because it's only 60% of such a of methane in this biogas. So what is the difference between biogas and natural gas? Because actually there are the same element. I mean the methane. I mean compound element. So there is the time. So the production method. The natural gas is produced by the time when the pressure, temperature also decompose this organic matter and make methane and heavier hydrocarbons. And biogas is, as we said, is the gases which are gathered, captured from this above this biomass which is decomposed. The second difference is the quantity. So here we have the natural gas, I think, because I don't see, yes, and here we have the biogas. And this is the statistics for, let's say, 2-3 years ago. And you can see that the biogas is about maybe a little bit more than 1% of natural gas. So two main differences is the production method and quantity. Hopefully, we can also hear that the production amounts of biogas is increased year by year. So this is our hope. But because it's a quite small amount of the biogas, we can blend it with natural gas, make it more friendly. And for example, some directive, EU directive, describe the target that by 2020, 10% of energy in transport and 20% energy for producing energy should be used with this renewable source of energy. It's a mix, but also then biogas can be used to improve these indicators. Okay, so the next difference with natural gas and biogas is the composition. Because as you can see, that's here we have only methane in biogas. There are two kinds of waste, so almost the same. But with natural gas, we have also the heavier hydrocarbons. And this is another advantage for biogas, because with natural gas, actually with liquid natural gas, we have the phenomena which is called aging. And aging is because the first compound which vaporizes is methane, and the composition is changing, and the heavier hydrocarbons left, so the parameters of the gas in the tank is changing. In case of biogas, we don't have the heavier hydrocarbons, so when we remove all of these impurities, we have almost pure methane. I think. Okay, the treatment process is to remove. We have to remove the water, of course, because water could make some hydrates which block the facilities, the infrastructure. We remove all acid gases, so H2S, C2O. Then we remove also the water. In the red box, we have this part which is for the natural gas, so we have to remove also these liquids, I mean the heavier hydrocarbons, and then we can the product to final compressions to achieve the liquid state of the methane. Okay, a little bit physics. So actually all compounds, all elements has three states of matter. We call them gas, we call them liquid, we call them solid, because in the room temperature and the atmospheric pressure, they have such a state of matter. But it depends on the internal heat. When we deliver a heat, we can pass from one to another state of matter. When we remove the heat, also we can pass. So here is the phase transitions. When we have a solid, when we increase the heat, internal heat, the particles start jingling more, and then we have liquid. So the process is called fusion. When we deliver more heat, more energy, then from liquid through vaporizations we can obtain a gas. In some temperature and pressure conditions, we can go directly from the solid to the gas, and it was called sublimation. And it could happen in the triple points, which will be discussed on the next slide, I think. Okay, so during the phase transition, we have some hidden latent heat, because, for example, when we have this phase, so we have solid, and this on the, on the left side we have the temperature for the water. On the right side we have temperature for the methane. So when we deliver the heat, we have increased the temperature. At 0 degrees we have the fusion, so melting, the ice is melting. And in this case, until we obtain all liquids, we deliver a heat which is called the latent heat, hidden. So after we achieve all water or liquid, then we can also warm up the liquid, And in this point and this temperature, for the water 100, for the methane minus 161.5 degrees, we have the next stop, the vaporization. So also when we deliver the heat, we do not increase the temperature, but we increase the amount of vapor. And then when we have only vapor, then we have also heat them, the gas, to the higher temperature. There are three properties which can describe the gas: of volume, temperature, and pressure. And there are three rules which describe, which govern this process. So we have the Boyle's law, which describe how the relation between the volume and pressure. Then we have Charles' laws, which describe the relations between temperature and volume, and also Guy-Lussac's laws, which describe the relations between temperature and pressure, but in the closest space. Okay, as we said, all substances or compounds has three states of matter. So here we have the typical phase transition diagram. And this blue line shows us the boiling temperature in different pressure. This boiling line is limited with 2 points, the triple points, where we have actually three states of matter. We have a solid, we have a liquid, we have a gas. And then we have, on the other end, we have a critical point. And critical point is the highest temperature in which such a substance has liquid form, liquid state. Behind this point, even if we increase pressure, it will always be a gas. Okay? A gas, the density will be the same like the liquid, but the pressure would be much higher. So the boiling temperature for different substances or fuel is as follows. It's of course in the atmospheric pressure. So water, of course, 100 degrees. There are the others hydrocarbons. Here we have CO2, and methane is boiling in minus 161.5 temperature, degrees of Celsius. And here is the same diagram for the methane, and we can see that the triple point is at temperature somehow like 188. Then we have the critical temperature about 82 degrees, which means that if we have methane, liquid methane in the tank, in the closed space, we cannot allow it to warm up more than this minus 82 degrees, because from pressure like this, about 45 bars, after this point we have 600 bars. So it's a quite dangerous situation. And yeah, the critical temperature for other fuels are shown on this slide. So, for example, ethylene has the temperature like a little bit more than 0 degrees. Of course, here we have the pressure. So methane, as we said, 82. Okay, for liquefactions, there are, on the previous slides was shown a few methods for liquefaction, for liquefy this biogas. There are some examples, for example, here for the unconventional gas solutions, which offer us a few types of facility. Just an example found by short browsing. So we have from 300 cubic meters per hour up to 3,000 cubic meters per hour. Here is the Wärtsilä's example, also scalable from 6 up to 50 tons per day. So there are solutions which can be used to produce locally liquid biogas. Okay, so now the biogas has different names. I mean liquefied biogas, so it's called bio-LNG, liquid biomethane, or liquid biogas. More often is used bio-LNG as a product. And of course, using this kind of fuels, we can reduce the greenhouse emissions. And this is, on this diagram, we have the comparison with the diesel. And when we take a diesel as a 100%, so in LNG, liquefied natural gas, we reduce emissions of CO2 by 20%. So it's 80% of the CO2 as is for the diesel. When we blend 17% of biogas, we reach the 63% of CO2 when we compare to diesel. When we use pure biomethane, biogas, then we can even have the negative numbers, but in conditions that we also the 30% of CO2, which is in the raw biogas, captured and used for other purposes. The other purposes can be, for example, producing synthetic methane using this CO2, for example, and hydrogen. And as a product, there is no difference in properties. So we have both LNG and bio-LNG as the same fuel, actually. And some of producers issue this safety data sheet, which is for the both such a liquid. In this case, we have gasum, I think. Okay, the characteristics of liquefied biogas, liquefied biomethane, is that we, during liquefaction, reduce the volume. In the gas status, we have 600 cubic meters. And when we compress and cool down to liquid state, we have 1 cubic meters. So we decrease the volume by 600 times. And during transport and storage, we do not increase the temperature more than minus 105 degrees Celsius. Then we have 20 bars. And the base is here, about minus 160 degrees, because this is the boiling temperature. It's almost atmospheric pressure. And another point is that when we warm up the LPG, the density of the LPG will be decreased. So here we have almost solid, minus 180 degrees, and the density is about 480 kilograms per cubic meters. In case of about minus 120 degrees of Celsius, we have less than 400 kilograms per cubic meters. And this is quite important because it could cause another phenomena like rollover. The batch difference could make such a also quite dangerous phenomena or situation. Okay, so LPG is extremely flammable. It means that even at this temperature, there is amount of vapor which can be ignited. But also, it's not means that that we have enough vapor to sustain this fire. Okay, it could flame for 5 seconds, but then disappeared because there is no methane in the gas state enough for sustain the fire. In order to burn, must be vaporized, mixed with air, with enough amount of oxygen. So there is very narrow proportions with air, and then ignited. The vapors itself is not explosives, but there is also some phenomena which called bliff. When we have closed space and we reach with this temperature more than 82 degrees, minus 82 degrees, then we have, as we said, immediate increase the pressure from about 50 bars up to 600 bars. And we have also, in case of maritime transport, I mean the gas carrier, we describe this liquefied methane as a low flash fuel, low flash point fuel, which is in the SOLAS one of the most important convention, is defined as a all fuel which has flash point lower than 60 degrees of Celsius. And okay, vapors are not explosives. Even if we ignite it, the flame is called lazy flame, so it's not explosives. Cold vapor up to minus 105 degrees is heavier than air, so will be on the bottom. So this is also quite a dangerous situation. When it warm up more than this temperature, it can be afloat up and dissipate with air. Okay, the flammability limit is quite narrow, from 5 degrees up to 15% in air. So below we have too lean, so will not burn because it's too low, too small amount of the fuel, of the methane. Above 15% we have too rich mixture, so too small amount of oxygen to keep a fire. The other fuels limits flammable range is on this table. So for example, hydrogen has the widest range of flammable, so from 4% up to 75%. In case of methane, as we say, 5% up to 15% of fuel in the air. Auto-ignition temperature. If we warm up the gas up to 537 degrees of Celsius, it could fire itself. But the high temperature is also caused that it cannot be used, for example, for the engine, diesel engines instead of diesel, because the temperature is too high. The other fuels, like diesel oil, the range is from 260 up to 371 Celsius, and gasoline also the range is lower than in case of methane. And energy units, traditionally we describe the energy which is in the fuel with joule or BTU, British Thermal Unit, which is defined like below. We have other BTU units with MBTU, it's 1000 BTU, BTU means million BTU. Also another equivalent is ton of oil equivalent. So for the diesel is about 42 gigajoule, this 1 ton of oil equivalent. So energy density is as follows. So we have a diesel, it's about almost 40 gigajoule per cubic meter. In case of bio-LNG also, LNG is almost a little bit more than half of it. And the density of other form of natural gas, biomethane, which could be compressed, it's 9 gigajoule per cubic meters. In case of natural gas, we have at atmospheric pressure, so 1 cubic meters has only, I don't see, 0.3, I think, something, gigajoule per cubic meter. Okay, the next point of this presentation is concern hazards of this fuel. And when compared with other fuels, of course, we have an energy. The fuel is flammable, so can cause a fire. In this case, we have also extremely low temperature. So all these hazards, we can divide it into 2 main groups for the personal injuries, so cold burns, asphyxia, and also for the infrastructure, so material cracking when we have a contact with big enough amounts of this liquid, the cryo liquid, we can make the steel very fragile and other also materials. The other hazard is bleed. I mentioned about this. So boiling, liquid, expanding, vapor, explosion. It's not explosion because the mixture was ignite and we have a flame, but it's because the temperature increase in the closed space and we have so pressure that the compartment would be broken and we have an explosion. So the health hazards is the burns, because it's a fire, frostbite, because of cold, and asphyxiants, because low amount of oxygen. As we said, when the vapor is cold, so below 105 degrees of Celsius, it's heavier than air and push out the air from the place where we normally live, so there is no oxygen to breathe. Other risks are described on the left side this table, and we have also what should be done in case of such a situation, and we have described it also in this data sheet. Was mentioned before. I think Marcin will explain a little bit more about this. And environmental hazard, bio-LNG rapid evaporation is expected from both land and water with no residues left behind. So when we spill LNG or LBG on the water or on the land, it vaporized very immediately. There is no rest on these surfaces. We cannot say that it's purely environmental friendly because methane is about 20 times stronger greenhouse gas, so of course have an impact on the warming climate effect. And but we can say it's not significant air pollutant. We don't have emissions like burning diesel or other fossil fuel. So you can say that even LNG and LBG itself is environmental friendly, but even LNG is quite environmental friendly because it's the cleanest. It's not, it still is fossil fuel, but it's the cleanest fuel from this group. When we spill on the water, it's vaporized also immediately. Do not harm any creatures below the water surface, and do not react with water. Do not make any substances. Sometimes it's danger when it's contact with chlorine. Reactivity with other substances, so with water. Of course, when we have at the same place, I mean, for example, in the pipe, some amount of water and liquid methane, of course, the water will be as a ice, could block some pipes, valves, and so on. Sometimes can create the hydrates. It's substances which looks similar to ice, but it's heavier than water, so wood can be below the surface. With air, of course, create a flammable mixture if there is enough amount of fuel and oxygen. So every time when we make some operations with tanks, we have to separate the methane with inert gas, for example, nitrogen. With other materials and with other cargo, we have always consider and consult with these data sheets, these two materials, two cargos, because we have to know if they are react with each other or not. So the same situations. And for example, for the gas carriers, always have to be considered the descriptions of the other materials, other cargo, what we should do. And ignition, explosion, flammability, hazard. So auto ignition is quite high temperature, but anyway, when the mixture, the flammable mixture, touch the surface which is high, so it's, for example, the temperature of this metal surface is higher than 500 degrees of Celsius, it could happen the fire. The flash point of a liquid is the lowest temperature at which the liquid will involve sufficient vapor to form flammable mixture with air. So flash point is the temperature in which we can make a fire, but not sustain fire. So for example, for a few seconds. Flammability, of course, the range of fuel and oxygen, or an air, which create a flammable mixture. So, when LNG, LBG, or bio-LNG is exposed to air, evaporates extremely rapidly, and we have, in very short time, we have explosive flammable mixture. And when we ignite this mixture, and if we have a pool of LNG, bio-LNG, we will have quite long period when the fire continue. and depends on the amount of bio-LNG, LNG, the fire, the flame could reach 150 meters high. We can see this flame, so it's visible. So about the flammability ranges we were talking already. So yeah, here is the diagram of interaction between the fuel, methane, oxygen, and inert gas, or nitrogen if you are talking about air. So this is the area in which we have flammable mixture in different proportion of these three elements, compounds. This red line is the composition in which all fuel and all oxygen is used to producing flame. So more or less is 1 to 2, so that the 33% of oxygen, 2 particles of methane. And here we have the line which describes the proportion with air, and here we have also this lower explosive or flammable limit and upper flammable limit. And this line also shows us the minimum amount of fuel, methane, which can produce the flammable mixture with air. Okay, as we said, we have the mixture, the vapor and oxygen or air, and if there is no ignition, there would be no fire, and we can expect that this all methane dissipate and afloat in a higher layer of atmosphere. But when during the vaporizing, during the time when the mixture is flammable and it meets this ignition source, we can have a fire. So, of course, naked light, smoking, spontaneous ignition, waste, somehow going hot and hotter, and hot work, cold work during any spark when we hit with something. Safety tools, aluminum sometimes can also, like leather, aluminum leather can cause the spark. Portable electrical equipment, and so on and so on. All this can ignite this flammable mixture. Also, electrostatic can cause the fire, and we have to avoid situation which can cause such a electrostatic discharges. So, for example, we cannot use CO2 directly to the pool of or to the vapor of methane, because as we said, when we have the pool of methane, the liquid methane, the vapor when is quite low above the surface, the temperature is about minus or less than minus 105 degrees of Celsius, and CO2 has the frozen temperature about minus 70 degrees, which means that when we put the CO2 in a gaseous state directly into this vapor, it could make an ice, and CO2 ice, of course, which due frictions can cause this also ignition. And also steam, metal reinforcements, and so on and so on. We have to follow these rules to to avoid these electrostatic discharges. Toxicity hazards, there is no, the methane is not poisons. So the main problem is because push out the oxygen with air. So we can experience asphyxiation. So this is the limit of breathable air. So below this amount of particle, methane particle, so 10,500 parts per million. And sometimes we can smell this the natural gas in our house because the operator adds some other substances like THT, which is extremely toxic. Of course, in proper amount. Okay, so when we have a pool, so spill with LNG, LBG, we will have some amount of liquid methane. Depends on the wind directions. We have the cloud. At the beginning, very close to the spill, we have overreach mixture. Then we have, of course, flammable, so the range is from 5 to 15% of the methane. And then we have also too lean mixture to be fired. So what's happened when we try to ignite this methane? When the cloud meets some ignition source here, the flames start and will go to this area and will flame, burn, and producing heat. The heat will produce more vapor, so the fire will also increase. When the ignition source will be somewhere here at the beginning, so the fire first go to the front of this cloud and then be at the same place like in the first example. Okay. If there is no immediate ignitions of an bio-LNG, LNG, a vapor cloud may form. There is, first of all, the lack of oxygen, so there is no breathable atmosphere. When spill occur in an open space, the liquid will rapidly evaporate to produce a vapor cloud, which will gradually disperse with downwind. And the vapor cloud or plume is flammable only over part of its area. So this is what was said before. The vapor cloud is long, thin, cigar-shaped. That depends on the speed of the wind and also the ambient temperature. So the speed of the warming up this methane and so on. So the cold vapor is denser than air at the temperature below minus 105 degrees. So initially we'll keep the ground. And the major danger from this vapor cloud occurs when it's ignited. Then we have, simply said, the fire. And the fire, of course, produces more vapor, which can sustain the fire, and the fire will become greater. But how to behave with such a fire will be told by, will tell Marcin later on. Extremely low temperature, so there is cryogenic liquids. So all substances which are not methane at this temperature can form an ice, for example, moisture. So synthesize water. And there is quite danger because we can break down the facility, the infrastructure. Of course, we mentioned also that when we pour directly into steel, there will be a shock, thermal shock. So we drop the temperature of such a substance, of such a infrastructure from, let's say, 20 degrees of Celsius rapidly to minus 160 degrees. There is no material which can be proof with such an experiment. So we will have brittle. The steel will become fragile and broken and untied. So everywhere when we expect some drops of liquid methane, we should protect it, for example, putting some tray below these valves, mostly with water, because when the drop is the drop of methane, liquid methane, touch the water, vaporize, but also condensate the water in the air, and we will see the cloud. And the cloud is not, of course, because of methane, but because of condensate moisture which is in air. Pressure hazards. To minimize danger of damage of the system, we should keep the tanks and also the pipes within this range of safety described by the producer. We should avoid opening very fast valves because we could cause this hammer shock pressure. And we should provide an instrument or facility which release the vapor from the tank if the pressure is too high. Okay, and we told also about this different density of the biomethane, liquid biomethane. And here we have some example because, of course, here we have the liquefied biogas, and this is sometimes even more amounts, percentage of methane. And where is it? This column. Here we have this. Okay, here. The last column shows us the density. So we can see that depends on the source, here natural gas, but also LPG. When we, for example, want to blend to make more friendly natural gas, we can achieve a quite dangerous situation when we have this batch difference. When we have one cargo, for example, so liquid methane, with, of course, specific composition, specific temperature, and then we add, I don't know if it will start, no. Can we, sorry? No, there is an animation. Could you, on the previous, oh, sorry. Here, okay. Okay, when we put the other cargo, of course, the other methane, then we have such a situations that even in previously, the lower layer is heavier and colder than the upper layer. After a while, because of the pressure of the higher layer, this become more saturated, so warmer and warmer. And there is some moment in which the lower layer is warmer and lighter than the upper layer. And they roll over. and release a lot amount of vapor. So this is rollover situations, rollover phenomena. We should avoid such situations, and to prevent these situations, we should mix or put the other cargo from the nozzle to improve mixing of these two kind of cargo. Okay. Another thing is BOG management, so boil off gas. We have to do something with this, and within transport through the sea, so for the gas carrier, there is quite a big problem because daily rate of vaporization is 0.10 to 0.15% of the all amounts. So when we have, for example, 1,000 cubic meters of such a cargo, we will have quite a lot amount of vapor, correct? It will be 1,000 cubic meters, 1,000 or 1 cubic meter with 100,000. Yeah, so about 1,000 cubic meters, 100, let's say, 0.10. Okay, so we will have to do something because during a long voyage, like a few weeks, there is quite a lot amount of vapor, and if we do not made anything with this vapor and keep in the tank, the pressure will increase, the temperature will increase. So we have to remove. By removing, we cooling down the rest of the cargo. And we have three methods to keep them at this boiling temperature. So the worst is to release to atmosphere, because when we release to atmosphere, then we have methane as a stronger gas in the atmosphere. We can use it as a propulsion. So all these BOG gases as a vapor should be processed and prepared to be used for engine, for the vessel engine. And it's happened very often, depends on the charter or the agreement between the shipper and owner of the cargo. Or reliquefaction. If there is a facility, we can reliquefy this vapor, but it's also cost. The cost of the fuel and also cost of the greenhouse emissions, because to reliquefy, we have to use the traditional fuel. So we increase also the greenhouse gases emission. But anyway, what it's done depends on the agreement between the shipper and owner of the cargo. In case of cisterns, actually we don't have the opportunity to reliquefy. So there is semi-pressure compartment which keep this methane in the pressure between 0 or 1 bar to 20 bars during the warming up, because anyway during transportations with this compartment, this gas will become warmer and warmer because the heat from outside will penetrate this tank. So in this case, we just have the release valves, safety release valves, which keep the pressure in this tank in the safety ranges. So the conclusions: LPG is odorless, colorless, non-corrosive, no-flammable, and non-toxic. So, as was said today, also it's a beauty fuel. It must be understood that the properties which make LBG as a good source of energy, it's also make it hazardous because it's a fuel. And in compared to the traditional fuel, we have also the very cold, extremely low temperature. All available storage and transportation temperature are considered as a cryogenic. It's always less than minus 120 degrees. LBG is renewable source of energy, and we cannot mix, we cannot treat LNG also as a LBG, but LBG can be transported, stored, and transferred with the same infrastructure which is used for LNG. So it's very easy to substitute this LNG, natural gas, liquefied natural gas with liquefied biogas. It's not flammable. LBG itself cannot be fired, but the vapor can make a flammable mixture. So we should ventilate well the compartment when the gas, the vapors, the low temperature vapors could appear. To large leaks and spills, we have systems, safeguards which can prevent and make warnings. Okay, so this is for the first part of this training. Thank you very much. I hope there is no any question. I think things are obvious. Thank you.
Good afternoon, everyone. My name is Marcin Przywarty. I'm representing mainly Maritime University of Szczecin, but today also Klaipėda Science and Technology Park. I have more than 10 years of experience related to the LNG, LBG, mainly because of the projects such as go-LNG or Martech. And today I will focus on the issues related to the safety of the handling, of the transportation of the LBG, and then I will explain. So maybe I will start with the information how we should handle, how we should treat the LBG to secure the safety, and then I will tell you what should be done or how we should behave if the accident happen. And of course, I will also explain what type of accidents can occur. Okay, so let's start with the contribution to the safe operation. Because the crucial part of the activity related to the LBG is transportation. I will focus on the transportation and the LBG, as the LNG can be transported by road, by rail, by inland waterways, and by sea. Of course, because of the volumes, the transportation of the LBG by the big LNG tankers is not very probable, but it is possible. I will also tell you about the regulations, which is about the transportation of the LBG by the sea. Okay, so let's start with the transportation by road, by rail, and by inland waterways. We have three main documents. Which we can where we can find the information about the transportation, about the rules. So for the road, we have the ADR, which is an agreement concerning the international carriage of dangerous goods by road. For the rail, we have the RID, regulations concerning the international carriage of dangerous goods by rail. and for the inland waters, we have ADN. And if we check the content, if we check the scope of those documents, we'll see that they are very similar. Of course, there are differences, but generally there are more or less. Generally, there are very similar. There are almost the same information can be found inside. The ADR consists of 9 parts. It is divided into 2 volumes, but generally we have 9 parts. In the part number 1, we have the general provisions. Part number 2 is a classification. Part number 3 is a list of the dangerous goods. Part number 4 is the packing and tank provisions. Part number 5, consignment procedures. Part number 6, requirements for the construction and testing of packagings and other types of packaging, so tanks and containers and so on. Part number 7 is the provisions concerning the conditions of carriage, loading, unloading, and handling. Part number 8, requirements for the vehicle crews, equipment operation and documentation. Part number 9, requirements concerning the construction and approval of vehicles. And if we compare the ADR with the RID and with the ADN, we'll see that the contents is almost the same. The only difference is that the RID has 2 parts less. The last 2 parts are not included in the RID. So, because the documents are very similar, I'll try to present the general rules together, to not split it into each way of transportation. I will tell about it all together. So, all 3 documents start with the general safety measures, and here we can find the general rules, not only for the LBG, not only for the LNG, but generally for the transportation of the dangerous goods. So we can find that all participants or parties of the carriage of dangerous goods shall take appropriate measures according to the nature and the extent of the foreseeable dangers, so as to avoid damage or injury, and if necessary to minimize their effects. And they shall in all events comply with the requirements, and when the risk occurs, the services, the emergency services should be notified, and all information should be given to these services. Then we can find the requirements for each party of the transportation. Generally, we have 3 main participants, 3 main parties of the transportation. So we have the consignor, carrier, and the consignee. And the consignor should hand over for carriage only goods, only consignments which conform to the requirements of the documents. The carrier who takes over the dangerous goods at the point of departure shall ascertain that the dangerous goods to be carried are authorized for the carriage in accordance with the documents. And the consignee has the obligation not to defer acceptance of the goods without compelling reasons, and to verify after unloading that the requirements has been complied with. Then we can find the more detailed requirements for the other participants of the transportation process. So we can find the requirements for the loader, for the packer, for the filler, for the tank container or portable tank operator, tank wagon operators, and the unloader. But I won't present it in details. The main part of all those 3 documents is part number 3. So maybe not the main. It is not most important. But if you want to find the information, we should start with the part number 3, where is the list of the dangerous goods. And if we find the proper line, proper entry, we can find the codes. In this list, we do not find all information, but we can find the codes. And here you can see the entries, the lines regarding the LBG. And I will now present the main points which can be found. Of course, there are some differences, but generally the information are the same. So in the first column, we can find the number. And for the LBG, the number is 1972. Is a UN number of the dangerous good. Then we have the name and the description. So the name is a methane, refrigerated liquid or natural gas refrigerated liquid with high methane content. Then we have the class, and the class code is number 2, which means that it is the gas. Then we have the classification code, which is 3F, which means that it is the refrigerated liquefied gas and it is flammable. Then we have the packing group, and there is no packing group assigned. Is this here? Yes, we do not have packing group assigned. Then we have the information about the labels which are required, and for the LBG, as for the LNG, the label which is required code, the label code is 2.1, which means this type of label, it is square, a little bit rotated, with the minimum dimension of 10 centimeters, and it should be red. And we can find the class, and as I presented on the previous slide, the class is number 2, and we can have the class symbol, which is the flame for the LBG, and it can be additional text in the middle, but in case of the LBG, there is no additional text. For the rail, for the trains, there is one more label which is required. It is number 13, and it looks like this. Is a triangle, upside down, let's say, with the exclamation mark. The black one and the minimum dimensions are also defined. Additionally, on the carrying the LBG should be marked with the orange-colored plate marking, which gives us the hazard identification number. Sorry. In case of the LBG, it will be 223, and the UN number, and as I said, it is 1972. We have also the minimum dimension defined, and the shape and the size of the numbers. Then we have the code for the special provisions. In this case, it is 392. It's special provisions when we carry the LBG or LNG not as a cargo, but as a fuel for the vehicle, which is fueled by this type of fuel. So it is not very common. Then we have the limited and expected quantities. In case of the LBG, the codes are 0 and E0, which means that it is not permitted to be carried as a limited quantity, and it is not permitted to be carried as an expected quantity. Then we have the requirement for the ADN, so for the inland waterways, we have the additional requirements. There is a carriage permitted, and the code is T, which means carriage is permitted in packages and in tank vessels. And for this carriage, there is a defined equipment which is required, and we have 3 codes. The code is PP, which means the protective that for each member of the crew, the pair of protective goggles, pair of protective gloves, and protective suit and suitable pair of protective shoes should be secured. And on board of tank vessels, protective boots are required in all cases. Then you have the code EX, which means that the gas detector is required, and code A, which means that the breathing apparatus, ambient air dependent, is also required. Then we have the requirements regarding the ventilation, and for the inland ships, there is an additional requirement that it should be equipped with the blue cone lights, and the number is 1. Then we have the more detailed requirements for the packing, for the tanks, for the bulk containers, for the ADR RID tanks, but I won't go through these codes because it is very detailed information about the pressures, about the sizes, the construction, and so on. Then for the rail and for the road, there is information what type of vehicle can be used, and then the code is FL, which is from the flammable, so the car should be prepared, should be suitable for the carriage of this type of cargo. Then we have the transport category, and the code is 2. Also information about the types of the tunnels through which the LBG can be transported, because it is not possible for each type of tunnels. To be honest, only tunnels of category A only through the tunnels of category A the LBG can be transported. Then we have the special provisions for carriage. And then we have the codes for the loading and unloading and handling. And we have the code CW9, which means that packages shall not be thrown or subject to impact. And there is additional requirement for the roads. Then we have the code CW11, which means that the receptacles should always be placed in the position for which they were designed, and be protected against any possibility of being damaged by other packages. Sorry. And then we have code CW36, which means that packages shall preferably be loaded in open or ventilated wagons, and if it is not possible, the marking, the information should be given on the door, warning, no ventilation, open with caution. Then for the road, we have additional requirement, which code is S2, which means that additional requirements concerning the carriage of the flammable liquids or gases, and there is a list of those requirements, but I won't go very deep to this. Then we have the carriage by sea, but as I said, it is not very probable to transport the LBG cargo by the big ships, but there is a code. The code is called IGC, the International Code of the Construction and Equipment of Ships Carrying Liquefied Gases in Bulk. So we can find the most crucial information about the construction, about the handling of this type of cargo. And I will focus on the chapter number 18, where we can find the operating requirements. The main goal, the most important goal for the IGC code is to ensure that all ships staff involved in cargo operations have sufficient information about the cargo properties and operating the cargo system so they can conduct cargo operation safely. Those involved in liquefied gas carrier operations shall be made aware of the special requirements associated with and precautions necessary for their safe operation. A copy of the code or the national regulations incorporating the provisions of the code shall be on board every time and every ship covered by the code, and the ship shall be provided with the copies of suitable detailed cargo system operation manuals, and the cargo operation manuals should include the information such as overall operation of the ship from dry dock to dry dock, including procedures for cargo tank cool down and warm up, transfer, including ship-to-ship transfer, cargo sampling, gas freeing, ballasting, tank cleaning, and changing cargoes, cargo temperature and pressure control systems, cargo system limitations, including minimum temperatures, cargo system and inner hull, minimum pressures, transfer rates, filling limits, and sloshing limitations, nitrogen and inert gas systems, firefighting procedures, operation and maintenance of firefighting systems, and use of extinguishing agents. Additionally, the special equipment needed for the safe handling of the particular cargo, fixed and portable gas detection, control, alarm, and safety systems, emergency shutdown systems, procedures to change cargo, tank pressure relief valve set pressures, and emergency procedures including cargo tank relief valve isolation, single tank gas freeing, and entry and emergency ship-to-ship transfer operations. The information about cargo, in our case, the information about the LBG should be carried on board, and the content of this information should include a full description of the physical and chemical properties necessary for the safe carriage and containment of the cargo, reactivity with other cargoes that are capable of being carried on board, the actions to be taken in the event of cargo spill or leaks, countermeasures against accidental personal contact, firefighting procedures and firefighting media, special equipment needed for the safe handling of the particular cargo, and emergency procedures. The physical data supplied to the master shall include the information regarding the relative cargo density at various temperatures to enable the calculation of the cargo tank filling limits, and the contingency plans which should be prepared for spillage of cargo carried at ambient temperature shall take into account potential local temperature reductions, such as when the escaped cargo has reduced the atmospheric pressure and the potential effect of this cooling on hull steel. What are the responsibilities? Of course, the person on board who is responsible is always the captain, always master, and the master shall ascertain that the quantity of characteristic of each product to be loaded are within the limits indicated in the International Certificate of Fitness for the carriage of liquefied gases in bulk, and in the loading and stability information booklet, and that the products are listed in the International Certificate of Fitness for carriage of liquefied gases in bulk. Care should be taken to avoid dangerous chemical reactions if cargoes are mixed, and this is particularly important when the tank cleaning procedures are required between the successive cargoes, and when the different cargoes are carried simultaneously at the same time. There are some additional requirements for the cargo at low temperatures. So when carrying cargoes at low temperatures, the cool down procedure laid down for that particular tank, piping, and ancillary equipment shall be followed closely. Loading shall be carried out in such a manner as to ensure that the design temperature gradients are not exceeded in any cargo tank, piping, and other equipment. If provided, the heating arrangements associated with the cargo containment system shall be operated in such a manner as to ensure that the temperature of the whole structure does not fall below that for which the material is designed. So some general information about the cooling. Generally, the tanks of the LNG, LBGD tankers are always cooled down. So even if the cargo is unloaded, some portion of the cargo stays just to keep the temperature. There is also information about the trainings for the crew members. And there are, let's say, 2 levels of the trainings. All personnel, so all crew members, shall be adequately trained in use of protective equipment provided on board and have basic training in the procedures appropriate to their duties, necessary under emergency conditions. And the officers shall be trained in emergency procedures to deal with the conditions of leakage, spillage, of fire involving the cargo, and a sufficient number of them shall be instructed and trained in essential first aid for the cargoes carried. That's all about the safety of transportation. So to conclude, we have 4 possibilities to transport the cargo. So we can transport LBG by road, by train, so by rails, by inland waterways, and by sea, by ships. And we have the documents, we have the agreements where we can find the information, where we can find the rules for the given type of transportation. Now I will explain, now I will present what we can do or what shall we do in case of the accident. So first I explained what can we do to avoid the accident, but now what we can do if the accident happens. The document where we can find the general information about the procedures is called safety data sheet. It was mentioned by my colleague. The safety data sheet is a document that lists information relating to the occupational safety and health. It should be prepared by the producer of the LBG, and should be provided to each buyer. The safety data sheet must always be available during transport and use and storage. In Europe, the safety data sheets are the part of the system which is called REACH, Registration, Evaluation, Authorization and Restriction of Chemicals. The SDS has, because it's a part of this system, it has the constant construction. There are 16 sections, and I will focus on the section number 2, where is a hazard identification, section number 4, first aid measures, and section number 8, exposure controls and personal protection. Here you can see the examples of the SDS prepared by different manufacturers, different producers. So first, the identification of the hazards. I won't dive very deeply into this topic because most of these hazards were presented by my colleagues. So we have the hazards related to the health, because the LBG has a flammable vapors. In high concentrations, it may cause slight dizziness and have an anesthetic effect. In even higher concentrations, because of the reduced amount of the oxygen, reduced consciousness and asphyxiation may result due to oxygen displacement, and long being in these conditions may result in unconsciousness and even death. Of course, because of the low temperature, it may cause severe freezing injuries on skin or on eyes. And for the safety hazards are generally related to the flammable explosive mixture of the LPG. So what we can do to reduce these hazards? To reduce these hazards, we can use the engineering controls. So we can provide adequate ventilation to keep gas and vapor concentration below the flammability limits. Generally, it should be less than 20% of the lower explosive level, so 20% of the 5%. Yes, because the lower explosive level for the LPG is 5%, so it should be lower than 20% of 5%. In confined spaces, local and general ventilation should be provided. We should follow appropriate confined space entry procedures, use the explosion-proof general ventilation and lighting in classified controlled areas, and we should be sure that explosion-proof flashlights and equipment are used. So it was the engineering controls. Of course, we also have to use the PPE, so personal protective equipment, for the eyes and for the face protections. The goggles or the face shields can be used. For the skin and hand protections, the workers, the operators should wear the thermal isolating gloves and clothing when working with the materials that present thermal hazard, hot or cold, in our case cold. We should ensure that the protective equipment is related for the temperature of the material to be handled, and the flame retardant clothing is recommended in any situation where LNG vapors may ignite accidentally. For the respiratory, so breathing protection, self-contained breathing apparatus or equivalent apparatus should be used when we know that there is low concentration of the oxygen, or if the concentration is unknown, and in situations that are immediately dangerous for life or health. If the accident happens, so if we have the contact of the LNG with eye, we should not, it can cause the frostbite. In case of frostbites or freeze burns, we should gently soak the eye with the cool to lukewarm water. We shouldn't wash the eyes with hot water, which is quite obvious. We should try, or we should open the eyelids wide to allow the liquid to evaporate, assuming that it is not a very high volume. So we can imagine that there is one drop of the LNG or the LPG. If the person cannot tolerate light, protect the eyes with the bandage or the handkerchief. Do not introduce ointment into the eyes without medical advice, and you should seek medical attention. If the contact is not with the eye, which is the worst scenario, but if the contact is with the skin, of course it also can cause the frostbite. In case of frostbite or freeze burns, we should remove the containment clothing and flush the affected area with cool to lukewarm water. We should not use the hot water or dry heat. We should seek medical attention, and under no circumstances we should should the frozen part be rubbed either before or after the warming. Just to maybe tell a little bit more, it is not like this that if we touch the LBG or if we touch the LNG, we will have the frostbites or frost injuries immediately. Generally, we can put the finger inside and take it away and nothing happens. So it is not like this that it is very, very dangerous that that the injuries are very probable. So it is possible to put the finger in it and take away. So if we breathe with the atmosphere, as my colleague said, the LBG, the LNG, isn't toxic. So the problem is only that the level of the oxygen is too low. So the problem is caused by not by the LNG, but by the low level of the oxygen, which is caused by the LBG. But LBG or LNG is not toxic. So inhalation of large quantities of LNG vapors may cause central nervous system depression with nausea, headache, dizziness, vomiting, and incoordination. LNG and associated vapor is a simple asphyxiant and may cause a loss of consciousness, serious injury, or death by displacing air, thereby resulting in insufficient oxygen to support life. Prompt medical attention is strongly recommended in all cases of inhalation overexposure. Rescued personnel should be equipped with the self-contained breathing apparatus. If we have the victims should be taken to the fresh air quickly. If inhalation victims is not breathing, we should ensure that the airways are open and administer cardiopulmonary resuscitation, so CPR. If necessary, we should have a trained person administer air or oxygen once breathing is restored, and of course we should seek medical treatment. There is one more hazard, one more danger, not very probable, but maybe someone will try. So if we try to swallow the LNG, so if we try to drink it, of course LNG is gas under atmospheric pressure, atmospheric temperature and pressure condition, and ingestion is unlikely, but if it happens, we should seek the medical treatment as fast as it is possible. The last part is the firefighting operation. So in this case, we have the leakage, we have the spill of the LNG or the LBG, and we have the fire. To have a fire, we should have the three conditions. So to make it possible to have a fire, the three components should be secured. We should have the fuel. In this case is LBG, and my colleague presented that the range of the flammability isn't very wide. It is rather narrow, between 5 and 15%. We should have the oxygen, and we should have the ignition source. The ignition source, it can be a spark, it can be an open flame, or it can be the high temperature. And the high temperature is the temperature of the auto-ignition. And because of the different composition, it can be more or less between 550, 600 Celsius degrees. LBG itself is not flammable because of the flammable limits. So in the liquid state, it is not explosive and cannot ignite. To become flammable, it must vaporize and mix with the air, and the range of flammability is between 5 and 15%. Because of the mainly because of the different place of the ignition, we can have, and the different pressures of the LBG, we can have the different types of the fires. So if you have those three parts, those three factors, and we have the fire, we can have the different fire scenarios. The first is the vapor cloud flash fire. The vapor cloud flash fire will occur if we have the late ignition. So ignition will be in the distance from the leakage. Of course, the vapor cloud should be the concentration of the methane in the vapor cloud should be between 5 and 50%, but in some distance from the leakage. In this case, not all cloud will fire immediately at once. The fire can burn forward to the cloud front or backward to the release point, so to the spillage. The speed of propagation, the speed of fire is not very high. It is more or less 10 to 20 meters per second. There is, because of this low speed, the overpressure isn't very high. So the serious consequences are possible only inside of this vapor cloud. Outside, the only problem is the high temperature. So close to this fire, it can be a problem, but it is not an explosion. Yes, it is just the flame. Of course, in the flames, we can have serious injuries, but only in the limited space. If the leakage is under pressure, we can have the jet fire. The jet fire occurs if the ignition of the liquid or the vapor of two-phase mixture is in the under pressure condition. Unlikely for the LNG storage tank, because normally it is stored in the atmospheric pressure, so there is no high pressures. But for the tanks, for the LBG, it is possible to transport it with higher pressure, so we can have the jet fire. It may be caused by the vapor leaking from the high pressure sources, so for example pumps, vents, risers or piping. It can be reason for the severe damages, and but limited to the confined to the local area. Then we have the pool fire. The pool fire is a fire close to the leakage area. Where you have pool, we have the vapors, and the vapors burns close to this pool, just above the pool. Because the leakage, the cloud can move together with wind, so the fire also will tilt in the wind and wraps around the obstacles, such as the front of the dike. In a diked area, fire will remain contained inside. Outside the confined area, fire is free to flow based on the topography, the shape of the area. For spills on the sea, the pool will spread to the steady pool size, and after the ignition, it will shrink. So, to conclude, if we have the spillage, if we have the ignition in a distance, we will have the vapor cloud fire, which can move to the place of the spillage or to the front of the cloud. We can have the jet fire in case that we have the higher pressure. We have the pool fire above the spillage. And of course, the vapor cloud fire can end with the pool fire or the jet fire. So it can transform from one type of the fire to the other one. Okay. Next type of the accident is the vapor cloud explosion. So it is called VCE. It is possible only in the confined areas, in the closed spaces. In this case, the flame speed will accelerate because of the higher concentration to form the deflagration type of explosion. It's not the detonation because the speed of the fire is below the speed of the sound, so it is not as dangerous as the detonation, but still can make a dangerous situation. But it only lasts with congested zone before flames decay to flash fire flame speed. So it is just the explosion for the short time. It is less damaging than the detonation because lower of speed, but can have a large impact, but only to the closed areas. Then we can have the belief. The belief was partly explained by Stefan, and as he said, it is possible for the pressurized flammable liquids exposed to an external fire when the unwetted metal over the vapor space in a container becomes weakened and fail, releasing the liquid that partially flashes to vapor. The flashing vapor expands and ignites as a boiling liquid expanding vapor explosion, so it is called belief. LNG is not pressurized normally, so there is a very low possibility of belief, but as I said, LPG can be transported in the cars, in the tanks, in the higher pressure, so it is possible for. The last part, which I want to present because of the shortage of time, is a firefighting plan. So this plan should be prepared in advance. It should be well prepared. What does it mean well prepared? But there's a general information that the firefighting plan should be well prepared. It should avoid the tactics hit and run. In most cases, in fact, the best way how we should behave in the case of the fire is to let it burn. If there is no, if the situation is under control, if there's no danger to the environment, to the people close to the fire, in most cases the best way of handling of the fire is to let it burn. The LNG will burn and nothing more will happen. And of course, we can try to cool down the surroundings. So we can use the water to cool down the surroundings and leave the fire to burn itself. If it is not possible to leave the fire to burn down, we can use the dry powder, and it is the best method of the firefighting, of the best method of the trying to stop the fire. Of course, if it is possible, we can use the fixed installation, but normally there will be the portable extinguishers. In the case of if you want to use the dry powder, we should use all possible dispensers at once. So do not try a little bit, maybe a little bit more, because it is not good. It is not good way of firefighting. So we should use all dispensers at once. The dry powder causes the flame to go out almost at once, but we have to remember that there is no cooling effect. We should avoid we should avoid to put the direct pressure of the powder jets on the surface of the LNG, because if we do it, we'll increase the rate of the vaporization, so it will be harder to extinguish the fire. Of course, we can use the water, but it is not very easy to extinguish, to stop the fire of the LPG with water. Generally, the water should be used mainly for the cooling down of the surroundings. So we can cool down the surroundings to stop to reduce the damages, but it is not very easy to extinguish the fire with the water. As it was for the dry powder, we should avoid the situation where when we put the water directly to the pool to the leakage of the LPG, again because of the increasing rate of the vaporization. So instead of the extinguish, we'll make the fire bigger. Yeah, and as I said, generally used for the cool down surroundings and essential for the protecting steel work. We can use CO2. CO2 will stop the fire because of the leakage of the oxygen, but it is possible only for the confined, for the closed areas, such as cargo, compressor rooms, electric rooms, inert gas dried room. Some general rules, some general procedure for the firefighting operation. First, we should isolate the source of the leak. If it is possible, stop loading, discharging, and shut down all manifold valves. Of course, sound the alarm. Then provide the protection for equipment and for the firefighters. As it was presented, attack fire with the maximum rate of application of dry powder. Do not agitate to surface of any pool of LNG. Remain on guard against possible reignition. The ignition is possible of the auto-ignition temperature. Even if we stop if we stop the fire, there are still some hot elements, so there is no fire. We stop the action, and then the mixture is between the 5 and 15%, and we have the source, and we have the oxygen. The fire can start again. All remedial measures must be situational. So there is no one best way to execute the firefighting operation. First, the firefighter should stop at the safe distance, minimum 100 meters from the accident site. Check the situation, check the size, the location of the gas leak, non-ignited liquids, fire in the gas phase, liquid phase. Check the wind direction and should attack with the wind from behind. Do not use the water on liquid leaks and on fire. Extinguish the fire with the powder if it is available. If possible, shut off escaping gas, liquid, and self-contained breathing apparatus, and full protective clothing should be also used in case of the fire of the LPG. And it was the last point of my presentation. Thank you very much. I'm almost at time.
Well, that was perfectly timed because it's actually 15 minutes past. Well done. Any questions at all? Suspect not. Okay. Fine. But thank you very much. And thank you also to you, sir. Thanks very much. It's not easy doing the post-lunchtime slots. So thank you for that too. We have half an hour break for coffee, and then we come then for our last part of the conference, which are 2 more presentations. So have coffee, and I'll see you in half an hour. Thank you. So let's start before everyone's gone. I'll hand over to Niels. Thanks very much, and yeah, all the best with your presentation. Here's your thing here, and it should come up automatically.
Okay, thank you very much. Now there. My name is Niels Heine. I have the opportunity to give the second last presentation for today. My name is Niels Heine. I'm from Rostock, from the Institute for Sustainable Economy and Logistics, and I will present on our project Decentralized Power and Heating Supply using Smart Office and Building Control Systems. This is one of the pilots within this project, Liquid Energy. Just a few words on the Institute. Our organization has a strong performance profile in sustainability management with a focus on promoting sustainable practices across various sectors, especially energy, tourism, transport. Over these multiple dimensions, we believe that by adopting sustainable practices, we can contribute to a more resilient and environmental friendly future. I am not a technician. I will focus on non-technical issues, although this is a technical project. Our project to build a decentralized energy supply system, we showcase with this power of decentralized energy system by combining bio-LNG powered CHP. CHP stands for Combined Heat and Power Plant. This produces simultaneously electricity and heat, and combined this with solar energy. We have actually created with this project or this tool a robust and efficient energy supply system. We integrated smart office and building control systems. It's called smart home, and with this integration, we added a layer of intelligence allowing for optimal energy management and cost savings. This is a comprehensive approach. This empowers buildings to become self-sufficient and sustainable energy hubs. We actually reused and upcycled an already used CHP, and that's also our impact on sustainability, carbon reduction, energy efficiency, and the use of advanced technologies to achieve environmental and energy goals. You see on the left the CHP, in the middle the solar energy, which we integrated, and then on the right-hand side the integrated smart home system. We had to make some technical modification, of course. It is necessary with the EcoPower system, which is a system we bought from Weiland to adapt the fuel supply system. LNG, you know, which is in a liquid state, requires specific handling and storage considerations. Therefore, a special LNG storage tank was needed and a vaporization system. Sorry. This system efficiently warms the LNG, allowing it to transition from a liquid to a gaseous state. We have additionally made some adjustments to the control and monitoring system of the EcoPower that needed to be involved. This modification should enable the seamless integration and synchronization of LNG fuel supply to ensure actually their optimal performance and efficient energy generation. We have a power output or electrical power output of maximum 4.7 kilowatt, and we have a thermal output of around 13 kilowatt. We added the solar energy to combined it with the CHP. That means that we have different or multiple advantages. This includes that we have a complementary energy generation and increased energy efficiency. We reduce actually the peak loads, and of course there's the carbon emissions are reduced, and we have actually financial savings and a longer and enhanced energy independence. This makes synergy. We reduce environmental impact. Then we actually added smart home elements in our management system, so that we can intelligently control the energy usage in this building. We utilize home automation features. We can optimize the energy consumption and enhance the overall efficiency. That's the final thing we wanted to develop. It doesn't look that great at the moment, but that's the final state. We have an integration of weather. We have an integration of room climate. We have an integration of security, access control, environmental things, so that we see what's happening outside. And the implementation of smart home technology offers lots of benefits. We have weather-based adjustments for optimal room climate. We have enhanced security measures, convenient access control, and environmental conservation through efficient energy management. And of course, the ability to create dynamic lighting and shadow scenarios. That's actually a modern and sophisticated office environment. What did we do? We implemented heating control sensors. We integrated for the window and door contacted, so that the smart home can automatically adjust heating and cooling settings. We have a presence sensor, so that's only heated or energy is consumed when someone is in the office. We have added temperature and humidity sensors, and that also allows us an energy efficient behavior. And we have actually a very comfort thing. But the most efficient or the most interesting feature is actually this one. You see the map of the Rostock region. The red dot, there's the office, and on the orange dot it shows where people who are relevant for these offices live. And the smart home implementation incorporates location sharing of the main users, allowing for personalized energy management based on their presence and preferences. By knowing the user's whereabouts, so that we derived that from the calendars and from their daily behavior, the system knows, okay, he's going to the office today or not, and the office shall then or will then start heating or will not start heating. And the combination of location sharing, calendar reading, and learning commuting patterns empowers the smart home system to proactively adapt the user's energy needs. Yeah, and coming to a summary already. We have built a comprehensive project that focuses on the integration of decentralized power and heating system derived by bio-LNG, combining this CHP plant, solar energy, and smart home automation. This aim, or our aim was to achieve sustainable and efficient energy management for buildings, reducing carbon emissions and optimizing energy utilization. By combining the energy source solar power, we have a reliable and efficient operation of the CHP plant, and we show the potential for decentralized energy systems, the way we generate, distribute, and consume energy. And last but not least, the implementation of smart home, including location sharing, calendar integration, and so on, shows a personalized approach and actually a quite longer running of the system, and we do need less energy for all about that. And that's our project. Any questions? No questions? So, Magda. We have not calculated it, but deriving this from other projects we already placed and we already have in use. For example, for short-term rentals, where the presence sensor states if there's someone in the rental or not. We have a energy reduction of about 30%. Any other questions? No. So let's Magda come up.
And then our last speaker, I understand this will be in Polish, correct?
Hello, everybody. Because I'm the last speaker, it will be a little change in our routine. I will keep my speech in Polish language, and it will be translated on English. Let's start. The title of my speech is Implementation of Natural Gas and Bio-Natural Gas as a Fuel on Small Vessels. I tutaj skąd to się wzięło, jaka była przyczyna? Przyczyny były dwie. Pierwszą przyczyną tego stanu rzeczy był gaz, który się ulatniał z przewożonych zbiorników drogą morską. Ten gaz, ponieważ częściowo zbiorniki odparowywały, robiło się coraz wyższe ciśnienie w zbiornikach, zamiast upuszczać w atmosferę, jak to pierwotnie robiono, i zanieczyszczać atmosferę, zaczęto próbować spalać w silnikach. W ten sposób stwierdzono, że dzięki takiemu spalaniu częściowo gazu, częściowo paliwa okrętowego, ciężkiego paliwa okrętowego, spaliny są czyściejsze, a jednocześnie zmniejsza się straty energetyczne, ponieważ nie upuszcza się gazu w powietrze, tylko jest spalany i wykorzystywana jest energia do napędu statku. Spróbuję teraz przełączyć. Drugą częścią, która wprowadziła gaz do napędu statków, jest Międzynarodowa Organizacja Morska, która wprowadziła coraz bardziej surowe nakazy zmniejszenia emisji z silników, a generalnie w ogóle ze statków. I dokładne informacje są zawarte w konwencji MARPOL w rozdziale 6, które ustalają limity NOx-ów, limity dla SOx-ów, pyłów zawieszonych dla silników morskich. Ponieważ szereg informacji już było wielokrotnie przekazywanych, to tych nie będę powtarzał, bo chyba nie ma sensu, pamiętamy. W każdym razie, podsumowując, najbardziej restrykcyjny jest trzeci poziom, który określa standard emisji NOx, zarówno jak i pyłów zawieszonych, jak i tlenków siarki dla silników nowo budowanych, jak również dla silników, które były wcześniej zbudowane. Ten poprawiony rozdział 6 konwencji MARPOL wszedł w użycie w 2010 roku i jest praktycznie przez wszystkich ważniejszych armatorów ratyfikowanych. W związku z tym wszyscy tego powinni przestrzegać. Oprócz tego konwencja MARPOL wprowadziła jeszcze większe restrykcje w niektórych częściach świata. To są tak zwane Emission Control Areas. To są strefy, w których kontroluje się i są wprowadzone jeszcze bardziej zaostrzone przepisy w stosunku do ogólnych przepisów na oceanach objętych konwencją MARPOL 6 rozdziałem. I w tych obszarach mogą być, jest przycisk do, jest, mogą być ustanowione dodatkowe ograniczenia emisji tlenków siarki, tlenków azotu i pyłów zawieszonych osobno lub mogą być wszystkie razem wprowadzone jako obowiązujące na tych terenach. Tu są pokazane te istniejące strefy kontroli emisji. Zobaczmy, że do tych stref, do tej strefy zaliczany jest cały Bałtyk. W związku z tym na Bałtyku musimy przestrzegać bardzo surowych norm emisji. Na Bałtyku emisja SOx jest znacząca i mamy tutaj przykład, jak dzieli się ta emisja w odróżnieniu od w podziale na rozmaite rodzaje statków. Zwróciłem uwagę na małe statki. Małych statków są tysiące na Bałtyku, dlatego też ich emisja, mimo że one są małe, jest znacząca. Dlatego też warto zastanowić się, w jaki sposób emisję z małych statków ograniczyć, tym bardziej, że te statki najczęściej pracują bądź są eksploatowane nawet dla przyjemności, bądź jako jednostki zarobkowe blisko brzegu, albo wręcz wewnątrz obszarów śródlądowych. Dlatego warto zająć się zmniejszeniem emisji z tych właśnie jednostek. W jaki sposób to zrobić? Czy modernizować silniki, czy może używać skruberów do oczyszczania spalin, a może używać mało emisyjnych paliw. Wydaje się, że najlepszym rozwiązaniem jest używanie albo niskosiarkowych paliw, co wymagane jest zresztą przez trzeci poziom konwencji MARPOL dodatkowego rozdziału, albo używanie paliw alternatywnych. Ponieważ gdybyśmy stosowali nawet skrubery, prawda, to co... Oj, przepraszam bardzo, troszkę za szybko poszło. Teraz w drugą stronę. Zaraz spróbuję to znaleźć. Gdybyśmy, nie ten przycisk, gdybyśmy używali, no nie świeci się, świeci się, normalnych silników bez żadnych zabezpieczeń, to zarówno pyły zawieszone, jak i związki siarki wędrowałyby wysoko w chmury, potem w postaci kwaśnych deszczów spadały na ziemię i z rzekami spływały do morza. W Co się będzie działo, jeśli będziemy oczyszczać spaliny, używając skruberów? Wtedy oczywiście część znowu pójdzie w powietrze i spłynie nam w postaci kwaśnych deszczów, ale już dużo mniej. Natomiast jeśli to będą skrubery pracujące w układzie otwartym, wtedy będą związki siarki wrzucane bezpośrednio do morza. Czyli będzie efekt taki dosyć marny, prawda? Nie o to nam chodzi. Dlatego też poza tym skrubery są wielkie. One mogą być stosowane na dużych statkach, natomiast przy swojej wielkości, przy wymaganiach nakładów energetycznych i przede wszystkim przestrzeni nie nadają się na małe jednostki. Tu jest emisja pokazana NOx, ale to też już było wcześniej pokazywane. Dlatego chyba najlepszą według mnie ideą jest zmiana paliw ropopochodnych na paliwa gazowe. Na natural gas albo jeszcze lepiej na bio-LNG. Wtedy byłby zamknięty zerowa emisja na zero. Jakie są zalety stosowania naturalnego gazu? Największą zaletą jest to, że redukujemy szkodliwą dla zdrowia emisję. Oprócz tego spalanie jest bardziej efektywne, jest mniej zanieczyszczona komora spalania w silniku i odpada cały system oczyszczania paliw. W związku z tym upraszcza się troszkę siłownia. Jeśli już stosować paliwa gazowe, to tak jak pokazywano poprzednio, najlepiej stosować to w postaci ciekłej, ponieważ w porównaniu do CNG objętość tej samej masy jest 600 razy mniejsza. Początkowo stosowano paliwa, zwłaszcza na dużych statkach, razem z paliwami ropopochodnymi i to były tak zwane systemy dual fuel. Prawda? Silnik był uruchamiany na paliwie ropopochodnym, silnik obciążano. Kiedy silnik się nagrzał, kiedy jego obciążenie wzrosło do 15–20%, uruchamiano wtrysk paliwa gazowego równolegle z paliwem ropopochodnym. To rozwiązanie zostało właśnie w ten sposób utrzymane jako dwupaliwowy system z uwagi na to, iż temperatura zapłonu gazu naturalnego jest dużo wyższa niż paliwa ropopochodnego. I dlatego też ta dawka pilotująca ma za zadanie być dawką, która spowoduje zapłon pozostałej części paliwa gazowego. I tu na przykładzie, który pokazuje w swoich opracowaniach Volvo, pokazane jest, jak wygląda sekwencja wtrysku w silniku dwupaliwowym. Najpierw jest wtryskiwany diesel oil, który ulega zapłonowi od sprężonego, gorącego powietrza. Do tego już palącej się części paliwa ropopochodnego dotryskiwana jest dodatkowa dawka paliwa gazowego, wymieszanie i spalanie mieszaniny paliwa gazowego i paliwa ropopochodnego. W ten sposób zawsze zostaje nam jednak skomplikowany system, nawet bardziej skomplikowany niż system jednopaliwowy i zostaje nam to wszystko, co jest złe przy stosowaniu paliwa ropopochodnego. Dlatego też postanowiliśmy rozpatrzyć inny system, żeby móc zapalić, żeby mogło się paliwo gazowe zapalić, rozpatrzyliśmy zastosowanie iskry, tak jak w silnikach benzynowych samochodów. Iskry zapłonowej, która będzie powodowała zapłon mieszanki powietrza i wtryśniętego do cylindra gazu. Przy takim rozwiązaniu będzie tylko jedno paliwo na statku. Silnik będzie uruchamiany i będzie pracował tylko na paliwie gazowym. Będzie bardzo czyste spalanie i gaz może być doprowadzany nie przy wysokim ciśnieniu, a przy ciśnieniu rzędu 2 barów do cylindra, prawda? W związku z tym przy niskim, bezpiecznym ciśnieniu. Ponieważ stwierdziliśmy, że w ramach naszego projektu, przystępując do pracy, że w Polsce nie ma takiej jednostki, która pozwoliłaby studentom, kadetom poznać przy pracy na obiekcie rzeczywistym obsługę instalacji gazowej i silnika gazowego, dlatego też postanowiono zaimplementować do zasilania gazem siłownię starej jednostki Magda 1, która tutaj, jak Państwo widzicie, już była wtedy w takim dobrym, ale nie bardzo dobrym stanie, może powiem bardzo nie najlepszym, przycumowana przy Training Center of Maritime University of Szczecin i czekała na nowe życie. Ta jednostka, kiedy wspólnie zastanowiliśmy się z kolegami z Maritime University of Szczecin, w którą stronę iść, jakie rozwiązanie zastosować, została przeholowana do stoczni, wystawiona na ląd i w zasadzie poddana gruntownej renowacji. Zastanawialiśmy się, jakie rozwiązanie przyjąć. Najprostszym rozwiązaniem jest takie, gdzie mamy zbiornik LNG, baterię zbiorników sprężonego gazu. Dlaczego, to zaraz powiem. Wymiennik ciepła, który pozwala odparować gaz ciekły i doprowadzić po redukcji ciśnienia do silnika. Silnik pracujący na gazie naturalnym przez przekładnię napędza śrubę napędową jednostki, w ten sposób realizując swoją funkcję. Bardziej złożonym, bardziej interesującym rozwiązaniem, które rozpatrywaliśmy, było takie, w którym silnik będzie napędzał generator, który będzie przekazywał energię do przemiennika i z przemiennika częstotliwości zasilany będzie silnik elektryczny, który bez przekładni już wprost będzie napędzał nam śrubę. I wreszcie bardzo nas frapowało najbardziej złożone, najlepsze, najdoskonalsze naszym zdaniem i najbardziej przyjazne dla otoczenia rozwiązanie, gdzie silnik spełnia rolę silnika, który napędza generator, który przez przemiennik ładuje baterię akumulatorów. Cały czas pracując na tym samym optymalnym obciążeniu, z tą samą prędkością, akumuluje się energia w baterii akumulatorów i stąd przez Power Control Module jest skierowana na silnik elektryczny i napędza śrubę. Przy tym rozwiązaniu silnik może być mniejszej mocy, w związku z tym, ponieważ nie zawsze jednostka używa swojej pełnej mocy, dlatego też może napędzać prądnicę, a będzie się energia akumulowała w battery pack i w razie potrzeby będzie większa lub mniejsza doza energii pobierana i kierowana na silnik. Niestety po rozpatrzeniu naszych możliwości technicznych związanych z konstrukcją Magdy i finansowych musieliśmy zrezygnować z tej, wydawałoby się, najbardziej obiecującej dla nas konfiguracji i zastosować najprostszą pierwszą. Ta najprostsza konfiguracja jest o tyle obiecująca, iż ewentualni armatorzy, małych statków, którzy chcieliby zmienić zasilanie swoich siłowni na napęd gazowy, są zainteresowani, tak jak z nimi rozmawialiśmy, możliwie najprostszą konfiguracją, tak żeby przeróbki były jak najmniejsze, co potwierdzało znowu konieczność tej pierwszej konfiguracji, najprostszej. Wadą zbiorników LNG, zwłaszcza na małych statkach, które czasami stoją dłużej w porcie, jest to, iż po pewnym czasie ciśnienie w zbiorniku zaczyna narastać na skutek tego, iż rośnie temperatura gazu. Gaz nie odparowuje, nie jest odprowadzany, w związku z tym nagrzewa się i jeśli ciśnienie przekroczy wartość graniczną, najczęściej otwiera się, tak jak to jest na większości statków dotychczas robione, otwiera się zawór bezpieczeństwa i część gazu jest upuszczana przez zawór bezpieczeństwa w powietrze, zanieczyszczając atmosferę. Żeby tego uniknąć, zastosowaliśmy troszkę inne rozwiązanie. Rozwiązanie takie, teraz zobaczę, nie ma tutaj, ale cofnę się, które tutaj widać, mianowicie zbiornik LNG połączony jest z baterią zbiorników sprężonego gazu. Jeśli wzrośnie ciśnienie do ciśnienia bliskiego ciśnieniu otwarcia zaworu bezpieczeństwa, można wtedy w sposób zautomatyzowany przez tak zwaną doprężarkę, czyli taką sprężarkę, która zasysa gaz odparowany, gaz z przestrzeni nad cieczą ze zbiornika LNG, odpompować, sprężyć i wtłoczyć do tych zbiorników jako sprężony gaz. W ten sposób mamy niezależne dwa rodzaje zbiorników, zbiorniki sprężonego gazu i zbiorniki ciekłego gazu. To rozwiązanie ma jeszcze jedną zaletę. Mianowicie w zimie, kiedy silnik i siłownia jest wychłodzona, może być zbyt mało ciepła pobieranego z otoczenia, aby odparować ciekły gaz pochodzący ze zbiornika LNG. Wtedy można uruchomić silnik na gazie z baterii butli sprężonego powietrza. Kiedy silnik się nagrzeje, kiedy będzie wystarczająco dużo ciepła, żeby uruchomić parownik, wtedy można przełączyć zasilanie na paliwo pochodzące ze zbiornika LNG i dalej już silnik może pracować na paliwie z dużego zbiornika LNG. Pierwotnie planowaliśmy posadowić zbiorniki LNG tu w tej ładowni, która jest nad siłownią, a w zasadzie troszeczkę za siłownią. Jednak kiedy zobaczyliśmy, jakie warunki dotyczące wentylacji zostały narzucone przez Towarzystwo Klasyfikacyjne, stwierdziliśmy, że około 30% mocy, którym dysponuje silnik, musiałoby pójść na obsługę wentylacji. Wydawało się to zupełnie irracjonalne. Poza tym zwróciliśmy uwagę na to, iż usadowione wewnątrz zbiorniki i sterowanie tymi zbiornikami wewnątrz ładowni byłoby niekomfortowe dla prowadzenia instruktażu z obsługi, ponieważ 2-3 studentów mogłoby wejść do środka. W związku z tym wynieśliśmy zbiorniki na pokład, tak jak tutaj pokazane. Oj, przepraszam. Tu jest bateria zbiorników czego mi się to przestawia, sprężonego gazu, natomiast tu jest zbiornik LNG i w ten sposób one będą przykryte daszkiem, ale można do nich podejść, obserwować. Wiele osób może stanąć w koło i każdy będzie widział, co się dzieje, każdy będzie mógł łatwo tego dotknąć, a jednocześnie odpada cały złożony system wentylacji, który w tym momencie jest niepotrzebny, ponieważ wentylacja jest naturalna. Tutaj jest pokazany schemat instalacji gazowej, zbiornik LNG, w którym można przez doprężarkę w przypadku wysokiego ciśnienia wewnątrz doładowywać, z niego można doładowywać butle sprężonego gazu. Z tych butli można kierować przez zawór szybko zamykający na reduktory i na silnik gaz i w ten sposób zasilać siłownię gazem, albo można jechać tą gałązką i zasilać również przez reduktory silnik. I ta idea została zrealizowana na Magdzie. Pierwsze obroty silnika i pierwsze próby silnika były wykonane rok temu w Krzeszkowicach koło Krakowa w firmie, która przerabiała to. I tu widzimy te elementy, które charakterystyczne były dla tegoż silnika. To są reduktory gazu wraz z podgrzewaniem, tu są wtryskiwacze i charakterystyczna zmiana w głowicy. W miejsce zaworu wtryskowego mamy świecę zapłonową. I teraz poproszę, silnik został przywieziony do Szczecina, zainstalowany, oprogramowano go tak, aby mógł pracować we właściwym polu pracy z tą śrubą i z tą przekładnią, która jest na Magdzie, i usłyszeliśmy pierwsze, jeśli można prosić, pierwsze próby, kiedy jeszcze było oprogramowanie puszczane, prawda, to jest to. Dźwięk silnika pracującego na Magdzie, na paliwie gazowym. Jeszcze to drugie, prawda, i można ten... I tu już próby eksploatacyjne pod obciążeniem. Silnik pracuje na Magdzie. Jeszcze jest dużo rzeczy, bo jesteśmy w trakcie regulacji, ponieważ trzeba było dopasować pole pracy do warunków pracy jednostki napędowej i śruby. Wykorzystaliśmy w naszym rozwiązaniu maksymalną ilość powtarzalnych, dostępnych na rynku elementów, takich jak reduktory, jak wtryskiwacze. Zastosowaliśmy elektroniczny sterownik EcoMaster, który jest sterownikiem uniwersalnym, z tym, że trzeba było do niego wykonać bardzo duże zmiany w oprogramowaniu, tak aby się nadawał do sterowania tym silnikiem, a nie silnikiem benzynowym, ale to zostało właśnie zrobione. I na tym skończę. Dziękuję za uwagę i jeśli będziecie Państwo w Szczecinie, a jeśli Magda już będzie na wodzie, to zapraszam na pierwsze treningi. Dziękuję bardzo.
So thank you very much for your presentation. I've got one question, because actually what we are aware of is the fact that from the technical point of view, it's possible. It's possible to make this kind of ships or vessels, small ships. Of course, this kind of small ships like Magda or vessels to use more clean fuel. The question is, because it's always, there are always two things, technical part and economic part. One of the aim of the project was also to test and try and yeah. So what do you think? Are all kinds of ships like this or does it make sense to just transform the engine to LNG, or it doesn't make sense from the economical point of view?
Okay, it depends, because we are on preferable situation with Polish register of shipping. And for us, it's not very cheap, but more cheaper than for other. And this is the one point of troubles. And the second is very simple, because it is connected with our way of reconstruction. Use the typical elements, use the cheap elements, but very good elements, really good. And it is not very high cost of replacement, technical replacement, but accepting it by PRS, it's not known to me, cost of accepting.
Thank you. Thank you.
Partner in crime. I suppose we are at the end.
We are.
And you are still fine.
Just looking for my document. Okay. Good. Yeah. Shall I just do a little summary and then I'll hand over to you. So here it says I should give a summary which lasts about 15 minutes, but I have no intention of talking for 15 minutes. Last 2 days, we've had a wide range of topics and discussions on future solutions, policies, and technologies. We've heard from a variety of organizations and individuals on a diverse number of topics under the umbrella of the bio-LNG market, challenges and opportunities for technology on the micro and nano scale. We've had some really excellent informative presentations, as well as good panel discussion yesterday, followed by further presentations and some training today. We've been able to sign a memorandum of understanding between parties, and have also been able to view one of the tangible outcomes of the liquid energy project, the mobile fueling station, and of course also the Magda boat. I certainly look forward to seeing how that fueling station will develop in the future, and when eventually it comes to market and is utilized, we can all say that we were able to witness its development. The conference has been attended by a wonderful mix of organizations and people from a variety of sectors, from across different countries and regions. Of course, the aim of the conference was to inform and to discuss and to network, to hear about challenges under this topic, as well as to hear about setbacks, but also, more importantly, about how those challenges are being approached on the way to achieving solutions and success in the future. And I'm sure that we can all say, those of us who are left here, that is, that we have broadened our perspectives and knowledge as a result of these last 2 days. Most memorable for me, funnily enough, was Michael's exercises yesterday. But as well, it was also the diversity of approaches, the commitment, the determinedness, the quality in approaching this common goal, which has been crystallized by the liquid energy project. That is not only discussing the challenges, but also the opportunities for having real impacts in terms of energy supply, and specifically the use of bio-LNG through innovative technologies. So thank you to everyone who's not only taken part, so a lot of our speakers have gone, but there are still some here. Thank you for taking part. For those who've been here on this stage, especially those who've also traveled long distances, some have already gone, of course. But also to thank the organizers behind the scenes. I mean those who's administered the conference, the organization that went on before, the tech team, the camera team, translators, and the many more that I actually don't know about. So that's it from me as the moderator of the conference. I have been really happy to have moderated for the last 2 days. I've enjoyed it, tried to put in a little bit of humor as well, but hopefully things ran quite well under my moderation. And of course, I'd like to thank Pavel as well for inviting me, for having me here, I'm going to hand over to him because I know he would like to say a few last words too. So thank you.
Yes, thank you very much, Justin. Justin Sismi, yeah, this is, so he was the master of disaster, let's say, and my partner in crime. But now to be a bit serious, I would especially I would like to thank, of course, Interreg South Baltic Program for co-financing this project. I would like to thank all partners of the project. I will skip right now listing them because you can really find all information on the website, on the project website. Of course, we shouldn't forget our YouTube channel and also LinkedIn profile. I would like to really thank to our technical team, Artur. Yeah, could you please show yourself? Yeah. So this is the person that was responsible for streaming, for recording, and yes, thank you, thank you. Konrad, Marcin, our camera team that allowed us to have a great documentation, and of course with under the leading of Justin. So thank you. I would like to thank all persons, all people sitting in front of this room, whole 2 days, spending time and sitting and giving a hand and helping whatever was necessary. I would like to thank Claudia for great assistance and really, really huge help. So thank you. And yeah, well, this is the end, I would say. We are all still fine and enthusiastic, and this is something that makes me really happy. So thank you very much. The liquid energy project goes to the end with the last day of June, so the activities. But we, after these 2 days, last 2 days, discussion with companies, with other organizations, we already know that there will be follow-up in one or the other way. So once again, thank you very much, Justin. It was a great pleasure for me to be here with you. And as I said, you are still fine after 2 days of hard work. So I would like to thank and send greetings to all people that are watching us somewhere in the world. So sending message in the bottle. And thank you very much for being here.
And have a safe trip back wherever you're traveling to as well. Exactly. All right. Thank you, guys.
Thank you. Bye-bye.
Bye.